Good morning, everyone. Welcome to Tech, AI, and Beyond. Thank you so much for joining us today. In our last deep dive, we explored the incredible world of sustainable manufacturing inside the Green Factory. Today, we're tackling what happens next. What happens once those products leave the factory floor? We are embarking on the journey to clean mobility. This isn't just about changing engines. It's about fundamentally reinventing how our world moves.
For more than a century, right, the internal combustion engine has defined what it means to be in motion. But that era is coming to a close. And our journey today is going to cover 4 key stages. First, we'll look at the electric revolution and what's next. Then, we'll explore the promise of hydrogen, especially for the heavyweights. After that, we tackle the toughest challenges, aviation and shipping. And we'll wrap it all up with the intelligence layer that makes everything smarter.
All right, let's dive right in. The electric vehicle has officially made the jump from a niche curiosity to a mainstream force. I mean, you see them everywhere now. It's really the most visible front in the battle for zero-emission transport. But the big question now is, what's next? Now that EVs are here to stay, what are the key technologies that are about to kick this revolution into its next gear? You know, the story of the EV is really the story of its battery. And this tells you everything you need to know. It shows the single most important reason EVs are taking off, the absolutely staggering drop in battery costs. Think about it. Back in 2010, a battery pack was over $1,200 per kilowatt hour, way too expensive for most people. But fast forward to today, and thanks to massive scale and new chemistries, that cost has plummeted by nearly 90%. We're getting really close to that magic number, $100 per kilowatt hour, which is the tipping point where EVs cost the same upfront as a gas car. That changes everything. So if that's where we are today, this is where we're going tomorrow. On the left, you've got today's lithium-ion batteries. They're amazing, no doubt, but they have their limits. That liquid electrolyte inside, it can be a fire risk, and it puts a ceiling on how fast you can charge. But on the right, well, that's the holy grail, the solid-state battery. By replacing that flammable liquid with a solid material, the benefits are just transformative. We're talking much safer, a potential 50 to 100% jump in energy density, which means way more range, and charging speeds that feel just like a 5-minute stop at the gas station. This isn't science fiction, by the way. Companies are racing to bring these to market this decade. A great car is pretty useless if you can't fuel it up, right? And it's the exact same for EVs. A solid charging infrastructure is what really kills range anxiety and unlocks mass adoption. And that infrastructure really has 3 tiers. Level 1 is just your standard wall outlet. It's slow, but it's perfect for an overnight top-up. Then you have Level 2, the standard for home and workplace charging, which gives you a full battery overnight. And then the big one, Level 3, or DC fast charging. These are the super-powered gas stations of the EV world, and they're what make long-distance road trips totally seamless. You need all 3 to make the system work. And look, when you talk about infrastructure, you just have to talk about Tesla. While every other automaker was focused only on building the car, Tesla did something truly brilliant. They built their own charging network right alongside it. The Supercharger network was designed from the very beginning to be fast, to be reliable, and to be perfectly integrated into the car's navigation. By solving this problem themselves, they didn't just help their customers, they built a massive competitive advantage. It's been so successful that it's now becoming the charging standard for everyone in North America. Just a masterclass in strategy. Okay, take a look at this number, 95%. Any guesses what this represents? This is the average amount of time a privately owned car is parked. Just sitting there, idle. For 95% of its entire life, this incredibly complex, expensive machine is doing absolutely nothing. And this staggering inefficiency, it's also one of the single biggest opportunities in the entire clean mobility transition. So how do we tap into that opportunity? Well, that brings us to a truly revolutionary concept called vehicle-to-grid, or V2G. The whole idea is to turn that idle 95% into a productive asset. See, V2G tech makes electricity a two-way street. Your car can charge from the grid, sure, but it can also be told to send a tiny amount of power back to the grid when demand is high. So just imagine thousands of cars plugged in at an office park. A heat wave hits, the grid gets stressed, and it can just pull a tiny bit of power from each car to stabilize itself. Suddenly, millions of cars become a massive, distributed, virtual power plant. It's a game changer for building a grid that runs on renewables. So, we've established that battery electric tech is a fantastic solution for passenger cars. But what about the real heavyweights? What about long-haul trucks, city buses, or even massive ships? The sheer weight of batteries needed for those applications just becomes impractical. And this is where the next stage of our journey begins, with the promise of hydrogen. Now, a hydrogen fuel cell vehicle is still an electric vehicle. The key difference is that it generates its own electricity on board. You can think of the fuel cell as its own mini power plant, and the process is just so elegant. As you can see, hydrogen gas comes in on one side, the anode. A catalyst there strips the electrons off, and that flow of electrons is the electricity that powers the motor. Meanwhile, the leftover protons pass through a membrane to the other side, the cathode, where they combine with oxygen from the air. And the only thing that comes out of the tailpipe? Pure water. That's it.
Okay, but here's the catch, and this is a really critical point. Not all hydrogen is created equal. Its actual benefit to the climate depends entirely on how it's made. Most hydrogen produced today is gray hydrogen, which is made from natural gas in a process that actually releases a lot of CO2. Then there's blue hydrogen, which is the same process, but the CO2 is captured. It's better, for sure, but the ultimate goal, the one we're really striving for, is green hydrogen. This is made by splitting water using renewable electricity from wind or solar, and that is the only way to get a truly zero-carbon fuel, from production all the way to the vehicle.
So why go through all this trouble for hydrogen? Well, this chart here shows you exactly why it's so compelling for heavy transport. For a long-haul truck, every pound of battery you add is a pound of cargo you can't carry. A hydrogen fuel cell system is much lighter, which means more payload. And second, and maybe even more important, is refueling. You can refuel a hydrogen truck in about 10 to 15 minutes, pretty much the same as a diesel truck. A battery electric semi, that could take hours. And in the logistics world, where time is literally money, that difference is everything. A lot of people might look at the Toyota Mirai, a passenger car, and say it hasn't been as successful as battery EVs. But that's kind of missing the point. Its true legacy is as a technology demonstrator. Toyota has spent decades perfecting the fuel cell stacks inside the Mirai. And now they're taking that exact proven technology and scaling it up. Through programs like Project Portal, they've put those Mirai fuel cells into massive heavy-duty trucks, proving the tech is tough enough and ready for the really hard work of commercial logistics. And now we arrive at the most challenging leg of our journey. Let's talk about the final frontiers, aviation and shipping. I mean, these are the connective tissues of our global economy, but they are incredibly difficult to decarbonize. The amount of energy you need to lift a plane and fly it across an ocean is just mind-boggling, and it's far, far beyond what today's batteries can deliver. This quote just says it all perfectly: the tyranny of battery weight. See, jet fuel is an amazing substance. It packs an incredible amount of energy into a very small weight. Batteries do not. Their energy-to-weight ratio is orders of magnitude lower. And here's the real kicker. As a normal plane burns fuel, it gets lighter. An electric plane has to carry that same massive battery weight from the moment it takes off to the moment it lands. This is a fundamental physics problem that makes long-haul electric flight basically impossible with the tech we have today. So if batteries aren't the answer for big planes, what is? Well, in the near term, it's all about sustainable aviation fuels, or SAFs. These are what we call drop-in fuels. They're chemically almost identical to jet fuel, so you can use them in existing airplanes and infrastructure without any major changes. They mostly come in two flavors: biofuels, which are made from things like agricultural waste or algae, and synthetic e-fuels, which you can create by combining green hydrogen with captured CO2. Cost and scale are still big challenges, but right now, SAFs are our best bet for cleaning up air travel. Now, while a battery-powered jumbo jet is still a long way off, electric aviation is actually becoming a reality by starting small. This right here is the Eviation Alice. It's an all-electric, 9-passenger aircraft designed specifically for short-haul routes. We're talking under 500 kilometers. By targeting this niche, they can build a viable, zero-emission plane with today's battery tech. And imagine these quiet, clean planes revitalizing regional air travel, connecting smaller towns and cities without all the noise and pollution. It's a really exciting space. All right, let's head out to the open ocean. Decarbonizing global shipping is another monumental task. The leading candidates to replace the heavy fuel oil used today are green ammonia and green methanol. And you guessed it, both are derived from green hydrogen. But alongside new fuels, we're seeing this really clever return to the past, but supercharged with modern tech. Things like wind assist systems, towering automated rotor sails, or giant kites are being installed on cargo ships to harness the wind and cut down on fuel use. It's this cool blend of cutting-edge chemistry and really ancient maritime know-how.
Okay, so we've covered the power batteries for cars, hydrogen for trucks, new fuels for planes and ships. But the final piece of this puzzle isn't about what powers the vehicle. It's about how smart the vehicle is. The question is, how can intelligence and autonomy act as a force multiplier, making the entire system not just cleaner, but radically more efficient?
And this brings us to a concept called transport as a service, or TaaS. Remember that 95% number, the time a car just sits there doing nothing? TaaS flips that completely on its head. Instead of owning a car that you barely use, you would just summon an autonomous EV on demand from a shared fleet. Mobility becomes a utility, something you just consume when you need it, like electricity. This means you get radical asset utilization. Instead of needing, say, 300 million private cars, you might only need 50 million shared ones to serve the same number of trips, because they're always moving, always working. The ripple effects here are just staggering. First off, you need way fewer vehicles, which means a huge reduction in the emissions from manufacturing them in the first place. Second, you can right-size every single trip. If you're commuting alone, you summon a small, super-efficient one-person pod, not a giant 5-seat SUV. And finally, think about what this does for our cities. If you drastically cut the number of cars, you can reclaim all that land currently wasted on parking lots and turn it into parks, housing, and vibrant public spaces. And beyond just the system-level benefits, autonomous systems are just better drivers than we are, at least when it comes to efficiency. They accelerate and brake far more smoothly, which saves a lot of energy. And they enable incredible techniques like platooning, especially for trucks. Using vehicle-to-vehicle communication, autonomous trucks can form these tight convoys on the highway. The trucks behind the leader face way less aerodynamic drag, and that can cut their energy consumption by over 10%. When you think about millions of miles, that's an enormous saving. And so, we reach the end of our journey, and we look at the road ahead. What's clear is that the path to a zero-emission transport future isn't some single superhighway. It's a complex campaign being fought on multiple fronts. Battery EVs are the winning solution for our personal cars. Green hydrogen is poised to power our heavy-duty sectors. And for those final frontiers of aviation and shipping, it's going to take a mix of sustainable fuels and new technologies. And then, layered over all of it, autonomy promises to make the whole system not just clean, but truly intelligent. So I think the key takeaway is this. There is no single silver bullet. Decarbonizing how we move requires a whole portfolio of solutions: electrification, hydrogen, sustainable fuels, intelligence, all working together. The amazing thing is, the technologies are largely here. The real challenge now is combining them with smart policy, investment, and the collective will to build a better future. The question is no longer if we can create a future of clean mobility, but really how quickly can we make it a reality. I hope this deep dive gave you a clear picture of the exciting road ahead. Be sure to tune in for our next session where we'll explore the digital ecosystem, intelligence, sensors, and trust. Thank you so much for watching. If you enjoyed this, please subscribe, like, and share, and don't forget to hit the bell for more from tech, AI, and beyond.